Hello, Chem 213 students, and welcome to our first lecture of this week on aromatic substitution reactions. And so in last week, we started to discuss certain reactions related to aromatic compounds, and particularly describing the special stability that aromatic compounds have. Now, generally, aromatics are unreactive, as we've seen in the last chapter, chapter 17, but they can be made to be reactive under the right conditions. And so, in chapter 18, we're going to be discussing those conditions under which aromatic rings can be reactive, particularly benzene rings, and what kinds of reactions they can undergo, in particular substitution reactions, along with some other related reactions. So in the last chapter, we've seen how aromatic pi bonds are less reactive than typical alkenes. For example, if you react an alkene with a halogen, a bromine or chlorine, you can, in particular bromine, you can get the anti-addition of bromine atoms where their stereochemistry is opposite to one another. But if you try the same reaction with bromine by itself, the reaction will not occur. So we need some type of a catalyst in order to make this reaction happen. The transition states here are just too high, and so the kinetics are very unfavorable. If you introduce iron into the reaction as a catalyst, a substitution reaction will occur in which a hydrogen atom right here, so there would be a hydrogen atom, let's say this one right here, there's in fact one hydrogen atom on every carbon, would be replaced with a bromine atom, and this is referred to as an electrophilic aromatic substitution. And the electrophile here will be the bromine, but the bromine by itself is not a good electrophile. It's the introduction of the iron that allows it to be a much better electrophile rather, and undergo this reaction. So this is a kind of reaction referred to as an electrophilic aromatic substitution, which will be the primary reaction that we're studying in this chapter. In this case, the ring here will act as the nucleophile, and the reagent here will react as the electrophile. It's just like any alkene, it will be providing the electron. So in an alkene addition, the alkene is the nucleophile. Under the right conditions, we can make the benzene ring behave like an alkene and also be the nucleophile. The electrophile will be the halogen in the presence of a catalyst or these other reagents here, which are catalyzed in their own way. The aromaticity of the ring will be preserved in these substitutions. So going back to chapter 8, we observed the bromination or the halogenation of an alkene. This halogenation occurred because the alkene behaved as the nucleophile, meaning that it was attracted to positive things. The electrons in this pi bond, they're much more weakly held than electrons that would be in a sigma bond, so they can be donated. And that makes the alkene behave as a nucleophile. The electrophile would be attracted to those electrons. Halogens can behave as electrophiles in alkene addition reactions because of their high polarizability, meaning at any given moment it is possible that there will be more electrons on one side of the molecule than the other. Particularly as they get close to these pi electrons, there will be a repulsion between the pi electrons and the electrons in the bromine molecule, thus pushing them away and having more negative charge on one side, thus having a partially positive charge on the other. And then that allows that reaction to initiate. However, in the case of a benzene ring, it does not behave as an alkene due to its additional stability. But what can be created by the introduction of iron is the iron 3 bromide. And this iron 3 bromide would behave as a Lewis acid catalyst for this reaction. This Lewis acid catalyst will make the bromine here electrophilic enough to be attacked by the more stable pi electrons that exist in the aromatic ring. So the way this occurs is, first of all, we should think here. So this mechanism here is going to be very important for this chapter. This chapter is going to have continued types of mechanisms that follow this same theme. And this theme is going to be in that there's going to be some type of electrophile here, this iron here, or Lewis acid to be more exact. Due to the fact that the bromine is much, much more electronegative than the iron, there's electron density pulled away from the iron. Therefore, the electrons that exist in the bromine that are relatively weakly held can undergo a Lewis acid base reaction in which the bromine here is the Lewis base and the iron is the Lewis acid and accepts an electron pair in making a bond to the bromine. Now, in this case, the iron has one additional electron, giving it a -1 formal charge. The bromine now is sharing this pair of electrons instead of having them exclusively, and that gives it 2 bonds and 2 lone pairs rather than 3 bonds and 1 lone pair, giving it a positive formal charge. Now, we can also observe this as a situation in which we have essentially an ionic compound. And this is in a sense there's a kind of equilibrium between these here. But if we write this in such a way that we give all of the electrons in this bond the bromine atom attached to the iron, we can treat now this bromine here as essentially being a cation, missing 1 electron. So bromine is in group 7, and we usually have 7 valence electrons. Here it is drawn with 6. So it is a bromine cation. And this bromine cation will now be the electrophile in the electrophilic substitution reaction here, the electrophilic aromatic substitution. And so this is going to be what accepts the pi electrons from the benzene ring, making it a much more potent electrophile than just the Br2 by itself. So after we have this electrophile now, this is going to react, and so here we have the same electrophile, the one here pictured in the middle. This is the electrophile. This bromine now is essentially positively charged, so we're also treating it, going back to the last slide, essentially like a positively charged ion. So it's going to be very, very attractive to these pi electrons, and now the the benzene ring will behave as a nucleophile in a similar fashion to how a alkene would behave. And so that we have now this nucleophile here is going to donate its electrons, its pi electrons here to the bromine to make a bond, and simultaneously this bond will break. This is a nucleophilic attack, and essentially is like a loss of a leaving group. And what is ultimately formed here is a carbocation, and this is because we get 1 bond to bromine. However, the other hydrogen here now has only 3 bonds and no lone pairs, because it had 1 hydrogen here, and that hydrogen is still there, but there was a double bond, and there's no longer a double bond there. So that's hydrogen. It's still here. We could draw it in if we like. But this carbon has 3 bonds and no lone pairs, so it is a carbocation. And so this carbocation is allylic at this point, because for this intermediate, there is no longer aromaticity. And so we have an allylic carbocation, which results in a resonance here. We can draw this arrow here, and now we'll have the pi bond drawn here, and this carbon will be drawn with 3 bonds and no lone pairs, giving it the positive formal charge. And we yet again have an allylic positive carbocation here. And so we can again do another resonance structure, and that puts the positive formal charge here adjacent to this hydrogen. And now we can undergo an elimination. Now, of course, the elimination could have happened at the beginning. What this is meant to show is that due to the allylic positive formal charges here, we have several different resonance structures, which stabilizes this intermediate and allows for a lower activation energy and allowing for this reaction to occur. At this point, we still have our now iron attached to 4 bromines with its negative formal charge. One last step will occur, and that step will be such that the 2 electrons that are making a bond between the bromine and the iron, that bond will be broken and instead will become a bond to this hydrogen, and simultaneously this will have essentially like a proton transfer from the carbon here to the bromine, and then this bond will break and we will recover our aromaticity by adding these electrons back on, and ultimately we get a stable halogenated product. Our other products are the FeBr3, which was a catalyst in this reaction and was recovered when the bond between the iron and the bromine was broken at the end, whereas it was formed at the beginning here. And we also get HBr due to this bromine protonated. So the first step here is that the aromatic ring attacks the electrophile. It creates this this resonantly stabilized intermediate, which is referred to as a sigma complex. And finally, we have the deprotonation of the sigma complex to give us back our aromatic stability here and lead to a stable product. Now, an addition reaction to an aromatic ring would be highly endergonic. Essentially, this is fairly easy to see here, because what we would do here is we would break the aromaticity of the ring. So we would lose all of that aromatic stability that we talked about in chapter 17, which would be highly energetically unfavorable. But instead, when we go through the sigma complex intermediate and we undergo a substitution, we recover that aromaticity, which gives us a lot of our energy back and ultimately ends up with a reaction that is exergonic, meaning it is negative in terms of delta G. Now, it's not just iron that can be used. Aluminum tribromide can also be used as the catalyst for the bromination. It would work in essentially the same way. Here, the aluminum would have the partially positive charge here, which would be attractive to the electrons in the bromine, and you would get the single bromination here. The mechanism is essentially exactly the same as when iron is used, except it's aluminum accepting the electrons from the Br2, not the iron. In addition, you can do this with chlorine as well. If you use aluminum trichloride, you'll get an 85% yield of the substituted chlorinated product here. Using F2, like many of the reactions we've discussed before, the fluorine will be highly reactive, and the reaction will be too exothermic and violent to be practical. And then for the I2, it will just simply be not reactive enough. It will generally be a slow reaction and will provide low yields. So again, it's the chlorination, the bromination that is the sweet spot here between these. Now, the electrophilic aromatic substitution mechanism for the chlorination is directly analogous to that of the bromination. So we get this intermediate here where the chlorine has the Cl2 has created a bond to the aluminum. This aluminum has an extra electron that it's sharing in this bond, giving it a negative formal charge. The chlorine now has essentially given away one of its electrons to aluminum. Thus, it is lacking an electron, or in other words, instead of having 3 lone pairs in one bond, which would be 0 formal charge, it has 2 lone pairs and 2 bonds, giving it a positive 1 formal charge. And at this point, the chlorine here behaves as the electrophile, and the benzene ring as the nucleophile. And again, it gives its electrons here to create a bond to this chlorine. We get a chlorine here bonded, and then for the other carbon, we have nothing bonded to it, so it's got 3 bonds and 1 lone pair. It's a carbocation. We get this same resonantly stabilized sigma complex, and when the aluminum trichloride with 1 additional chlorine attached, the product that is produced from this reaction here reacts, you have a proton transfer where the proton then becomes attached to the chlorine atom, and we have now the removal of the hydrogen, and these electrons here in this sigma bond go into the pi bond here between these two carbons, and our aromaticity is restored, thus giving us a stabilized product which has substituted with chlorine. Now, all of the electrophilic aromatic reactions discussed in this chapter are going to follow the same general mechanism. The benzene ring will behave as the nucleophile. There will be some positive electrophile. It will undergo a nucleophilic attack from the benzene ring. There will be the formation of this resonantly stabilized sigma complex, and then there will be some type of base that will remove a proton, doing essentially like a proton transfer, which results in the restoration of the aromaticity of the ring. What differs is going to be what is added on. It won't always be a halogen atom. There are lots of other groups that can be added on using this electrophilic aromatic substitution mechanism. For example, we can do what's known as sulfonation. Sulfonation is when we attach SO3, H here, to the aromatic ring. This occurs by using fuming sulfuric acid. Fuming sulfuric acid will decompose into sulfur trioxide and water. So it produces sulfur trioxide, and what you can see here is when it's drawn as this Lewis structure, we have 3 double bonds, but really the oxygen pulls the electrons so much that really they're much more towards the oxygen than they are the sulfur. And what this means is that the oxygens are all like a little bit more negative, and the sulfur in the middle has a pretty big partially positive charge, making it the electrophile in this reaction. So it's going to be the benzene ring attacking the sulfur atom in this case to initiate this reaction. Another reason why this reaction occurs so readily and why SO3 is such a good electrophile is that the sulfur atom has even more significant partially positive charge due to the inefficient pi overlap between the oxygen and the sulfur atoms. So the sulfur has a larger, almost sp3-like, it's somewhere in between sp2 and sp3 orbitals here, whereas the oxygen here has the smaller sp2 orbitals. So their overlap is not very good. It's better when the orbitals are of similar size. So the SO bond has significant single bond character. I think it's a little bit easier just to think of the electronegativity and how these electrons in these pi bonds are not very evenly shared between the oxygen and the sulfur. The oxygen is much more electronegative and will pull its electrons its way. Finally, the mechanism is going to go, as I said, in the same general pattern as before. We're going to have the benzene ring behaving as the nucleophile. The sulfur trioxide here, the sulfur is going to be the electrophile. Now this sulfur is already making 6 bonds, which is the maximum that it can make. And so we have to also use this arrow here to indicate the electrons here in the oxygen atom, giving it 1 bond and 3 lone pairs, so thus a -1 formal charge. There's a positive formal charge on this carbon here because the SO3 attached here, and so this carbon has 4 bonds, so this only has 3 and no lone pairs. We have a sigma complex like before, which is stabilized due to the resonance. In this case, the base here that removes the proton to restore the aromaticity will be water if this is occurring in aqueous conditions. And there will be a proton transfer restoring this aromaticity. Finally, notice that this oxygen here is negative. We can recover now our water here in this case, water essentially acting like a catalyst. After that, this oxygen here undergoes another proton transfer, thus protonating it and making a neutral compound instead of an ion. Now, sulfonation is sensitive to the reagent concentration, and it is reversible. So much like what we saw with addition reactions, so you can make a direct analogy here to addition reactions. In this case, we have the concentrated sulfuric acid. It's going to promote the addition, whereas if we have dilute, it will promote the elimination here. We'll discuss this process more later, a little bit later in the slides. We can do a similar reaction called nitration. Here we use nitric acid here as a source of the electrophile. The H2SO4 is going to behave as the catalyst, and it's going to behave as this catalyst because it's a stronger acid than the nitric acid. So it's going to actually donate a proton to the nitric acid and promote the formation of a so-called nitronium ion, which is going to be the electrophile in this reaction. And then at the end, what you'll have is a nitro group installed to the ring. So the first step here is to protonate the nitric acid, to further protonate it, and to ultimately produce this nitronium ion. So the first step in this protonation is a proton transfer between sulfuric acid, extremely strong acid, pKa -7, and then we're going to, so proton transfer always has two arrows, one arrow from the lone pair to grab the protons, and then the other arrow to leave both electrons behind, bond between the hydrogen and whatever it was bonded to. When this occurs, now we have this oxygen will be creating 3 bonds with one lone pair, so it will have a positive formal charge. At that point, we can have the removal of water by the movement of these electrons to produce a double bond with the nitrogen, and then finally the loss of water as a leaving group here, which is now a good leaving group because it has been protonated. That's why it did not occur before. Hydroxide would not be a good leaving group. Water is. It's neutral when it leaves. And then we have each oxygen here doing 2 bonds and 2 lone pairs, so they have 0 formal charge. But the nitrogen has 4 electrons to it. If we do the formal charge thing and we give nitrogen 1 dot for every bond, we'll see that there are 4 dots in its region, whereas nitrogen would usually have 5 dots as a normal nitrogen atom, 5 valence electrons, so it is lacking 1. So this nitrogen has a positive formal charge, and so it's going to be attracted to the electrons in the benzene ring, and it's going to behave as the electrophile. So we're going to have the same reaction mechanism as we had before. The benzene ring is the nucleophile. In this case, the electrophile is a nitrogen atom on this nitronium ion. So we have a nucleophilic attack from the benzene ring onto that nitrogen atom. Now, nitrogen cannot have 5 bonds, so we have to write a second arrow here showing those electrons going to the oxygen atom. And at that point, we have NO2 attached right here. But at this carbon here, we have now 3 bonds and no lone pairs because there's a hydrogen right here. Same as before, essentially, just with a little bit different electrophile here. And so this carbon has 3 bonds and no lone pairs. It's positively formal charged. We get this resonantly stabilized sigma complex, and the reaction is completed when this intermediate is deprotonated by water again. So that we have a proton transfer where the lone pair here in the oxygen makes a bond with the hydrogen, and then the 2 electrons in the sigma bond are left behind, and that restores the aromaticity, which again is favorable for this reaction because you get a much more stable product. And so this reaction becomes endergonic and spontaneous. Or sorry, exergonic and spontaneous. Releasing negative delta G. Now, if you have a nitro group, you can reduce this nitro group to form an amine. The reagents here are going to be iron or zinc and HCl, followed by NaOH. And the NaOH is going to be to deprotonate the amine because we need the acid here to catalyze the reaction. But if we have this in an acidic environment, we're going to get a protonated amine. That amine will instead be this nitrogen, and you'll have it's protonated like that, so it'll have a positive formal charge with 4 bonds and no lone pairs. So the hydroxide here is introduced in a second step to deprotonate that amine. So the overall steps for starting with a benzene ring and creating an amine are the nitric acid and the sulfuric acid to introduce a nitro group, NO2, and then reduction with iron or zinc in the presence of an acid, HCl. Finally, the deprotonation of that protonated amine by NaO. Now let's talk about alkylation. So we can use alkyl groups in addition as electrophiles. Now, we know that generally alkyl halides are electrophiles, right? And those alkyl halides would react with other nucleophiles. However, benzene is not a particularly great nucleophile, right? It doesn't undergo normal nucleophilic reactions. However, if we introduced aluminum trichloride, we can have an analogous reaction as we had with the halogenation, and we can install an alkyl group instead of a halogen atom. Now, normally these are nucleophiles. Alkyl halides are already good, decent nucleophiles, and this is because they have a polar bond here, and the electrons are pulled towards a halogen atom, making that halogen partially negative, and the carbon that it's attached to partially positive. However, even though these are pretty decent electrophiles, the benzene again isn't a great nucleophile, so we have to help this reaction along. And the way we help this reaction along is we have an analogous reaction to what we had with Cl2. So when we had Cl2, I'm just going to make here an analogy to Cl2. When we had Cl2, we had a reaction where the chlorine here did a Lewis acid base reaction in which it donated electron pairs to the aluminum. However, instead, in this case, it's going to be the chlorine that's attached to the alkyl halide that is going to donate the electrons. And so you get an aluminum that is going to have a 4th bond, so it will have 1 extra electron compared to when it had 3, giving a -1 formal charge. The chlorine now, instead of having 1 bond and 3 lone pairs, is going to have 2 bonds and 2 lone pairs, thus giving it a positive formal charge. And we can essentially, because of the large electronegativity difference between the carbon and the chlorine, we could alternatively draw this structure in such a way that we're saying that the chlorine is getting more of the electron density here, significantly more than the carbon. We give the chlorine all of the electrons here. We see that we have a carbocation. This is going to be our electrophile now, instead of it being a positively charged halogen atom like before. It's going to be a carbocation, a positively charged carbon. And this is going to be the electrophile, this carbocation, for this alkylation reaction. So it's going to be the same mechanism as before. You're going to notice this is really only one mechanism we've talked about. Even though we've seen it in various different forms, it's still the same mechanism. It's the benzene ring behaving as the nucleophile and doing a nucleophilic attack on the electrophile, which is positive in some form. In this case, the electrophile is the positively charged carbon atom here. And then we get an intermediate, the same intermediate sigma complex, because the other carbon atom here is making 3 bonds with no lone pairs. This sigma complex is stabilized by resonance. Afterwards, the ending is just the same as the ending we had with the halogenation, the halogen substitution, in that we have a bond between aluminum and chlorine. This is giving aluminum 4 bonds, giving it this -1 formal charge. We have a proton transfer where the electrons used for the sigma bond between aluminum and chlorine instead become a sigma bond between hydrogen and chlorine, and then the electrons that are here with between the hydrogen and the carbon are left behind, producing re-giving us or restoring this this aromaticity here, and getting us our aromatic ring back. This is referred to as the Friedel-Crafts alkylation. But notice it's the same mechanism we've been seeing time and time again. The real difference is that instead of having Cl2 here and that behaving as the Lewis base and reacting with the Lewis acid aluminum trichloride, it is the alkyl halide doing that and producing the carbocation as the electrophile. Now, if we have primary alkyl halides, this is going to work as well. So here we have an example of chloroethane. And if we have chloroethane, this is just going to work just fine here. We'll have the chlorine here do the Lewis act as a Lewis base in this reaction with aluminum trichloride. And again, we get this positively charged carbon that will be here if we were to draw it with the extra arrow where they separate as ions. And so this is going to be the electrophile. The problem is that many primary alkyl halides can undergo rearrangement. If we have chloroethane here, well, we don't have to worry about a rearrangement because both carbon atoms are going to be primary carbons. However, if we have a longer chain, hydrocarbon chain, now there's the potential for a rearrangement of the carbocation intermediate, right? So here in this case, we have again the Lewis-based donation of the electrons to the aluminum trichloride. This aluminum now has an extra electron with a negative formal charge. The carbon is making two bonds with two lone pairs, giving it a positive formal charge. Now, remember, we can write this. Another way to write this would be with the here this guy being a primary carbocation here, and then with these electrons over here, this chlorine would be neutral, but we'd still have the aluminum trichloride with the aluminum with the -1 formal charge due to the fact that it has 4 bonds instead of 3. And so we can see that a little better when we draw it this way. We're going to have a carbocation rearrangement, which ultimately gets us this secondary carbocation like that, right? And then the AlCl4 minus, that's all of this right here. And so now the secondary carbocation would be our electrophile, and you're going to get a rearranged product here. You'll get some of the product that involves this carbocation, so this can be undergo an attack here, nucleophilic attack by the benzene ring to produce the primary benzyl alkane chain here. However, also, and even more predominant, is going to be a rearrangement to produce a secondary carbocation and then a subsequent nucleophilic attack by the aromatic, which is going to produce for us the secondary product here, where we have now the carbon is attached on the second carbon rather than the first. So that is one limitation to Friedel-Crafts alkylation. You have to be careful doing this with primary alkyl halides that are not, chloroethane or bromoethane. If they are larger, you can have a rearrangement to the much more stabilized secondary carbocation. And again, in the case of chloroethane here, even if we had a rearrangement, we'd still get a primary carbocation. So we don't have to worry about that with the chloroethane. But we do with any longer hydrocarbon chains. We'll get a mixture of products here. All right. Now, there are other limitations to the Friedel-Crafts alkylation here. First of all, the alkyl group cannot be a vinyl alkyl group on the electrophile. This will result in no reaction. It can also not be aryl, and this is pretty obvious because if it were attached there, the intermediate would be a vinylic carbocation, which is very unstable. And even more unstable would be the aryl carbocation. So if we had the aryl carbocation here, this would be extremely unstable as well. So if you need to have an alkyl halide, not a vinyl halide here or an aryl halide. Those will not work. Also, whenever this happens, we have the potential for polyalkylation. So instead of just adding one alkyl group, here we may also add another. Okay, so that's another limitation here. Finally, the other limitation is that if we have some substitutions on the aromatic ring, this will deactivate the ring for reasons that we'll discuss a little bit later in this chapter. And the Friedel-Crafts alkylation will not work in that. And so now let's look at the Friedel-Crafts acylation. Friedel-Crafts acylation. So before our electrophile here was a carbocation, alkyl carbocation, and but what we can also have is a carbocation on an acyl group, and this is going to be even more stabilized due to resonance with the carbonyl here. And so the way we do the alkylation is the same as we do the acylation, but instead of having an alkyl halide, we're going to have an acyl halide here, with the halide attached to the carbon that is double bonded to the oxygen. And this is going to produce for us an acyl benzene ring. So how does this work? Well, it works in a directly analogous fashion to the alkyl halide electrophilic aromatic substitution. So before it was just, in the previous example, it was like a alkyl halide that was attacking. But this time instead, it's going to be the acyl halide that's attacking. But directly analogous, okay, mechanism, okay, no difference here. I'm going to erase this because we're talking about acyl instead of alkyl. But no difference here. The real difference is in the intermediate that is produced. So before we had a carbocation of some kind, but now we're going to have instead what's known as an Acylium ion. And this will occur when we draw, or we can see how this would occur when we draw this as an ionic compound here. Instead of the positive formal charge being in the carbon, we give, or the chlorine rather, we give this chlorine both the electrons here, giving it three lone pairs and one bond. The aluminum is still making 4 bonds, and so it has a -1 formal charge. But this carbon is now making 3 bonds with no lone pairs, so it has a positive formal charge. And this is referred to as the Acylium ion. And this Acylium ion is particularly stable because it has a stabilized resonance structure, and that is the one in which we write the lone pair, instead of being as pi electrons here, we write them as being attached to the oxygen here, which puts a negative formal charge on the oxygen, which is more stable. It also gives, let's see, or rather, sorry, I went the wrong way with that one. I should not be thinking here of the negative formal charge. I should be thinking more of the octet here. So if I go like this carbon is lacking an octet. It has 3 bonds, so it would be much more stable if it had an octet. That could be created by this triple bond with oxygen, which would leave a positive formal charge on the oxygen. So here's the resonance stabilization of the Acylium ion. The Acylium ion will be resonantly stabilized, again, because the lone pair in the oxygen here is involved in resonance. It's delocalized and partially on the carbon. So this gives the carbon here 4 bonds and no lone pairs, meaning it has no formal charge. It also has an octet, which is much more stable when carbons and nitrogen and oxygens have octets. And this leaves an oxygen with 3 bonds and 1 lone pair, so it has a positive formal charge. One note is that because they're resonantly stabilized, they're not subject to rearrangement. The rearrangement would be a less stable structure than the one we already have. So at this point, it's going to be the Acylium ion here that's going to be the electrophile. Again, the benzene ring is the nucleophile. And so there will be a nucleophilic attack of the benzene ring here on the carbon atom, which will behave as the electrophile. And then simultaneously, because the carbon cannot make 8 bonds, we don't want to draw it with 8 bonds, we simultaneously put these electrons back on the oxygen here. And so now this oxygen has 2 lone pairs instead of 1, and instead of having a triple bond, it's a double bond here. And this carbon has 4 bonds and no pairs. Now this carbon here, again, it had 4 bonds and no lone pairs, but now it only has 3 because it's no longer in a double bond and no lone pairs, so it's a positive formal charge. And we have the same sigma complex that we've been seeing again and again, which contributes to the stability of this intermediate. And finally, this is occurring in the AlCl3, and we have the AlCl4 minus 1 with the additional chlorine atom attached, and we have the same proton transfer, giving us HCl and recovering our aromaticity, and so we get the acyl aromatic group. Some alkyl groups cannot be attached to the ring by a Friedel-Crafts alkylation because of rearrangements, but an acylation will never rearrange because, again, there's a special stability to the Acylium intermediate ion. This Acylium intermediate ion has a stability that a rearranged product would not have, because you'd end up with a carbocation that is not resonantly stabilized. And so the result is that if you want to make sure that you get no mixture of products, but you attach the benzene ring to an alkyl group at the primary position, what you can do is an acylation, like we just saw. So we use an acyl group with AlCl3 here, with the acyl chloride here. And then after that, we do a full reduction where we completely remove this oxygen ion. This can be done with a zinc and mercury amalgam under acidic conditions, and heat will ultimately produce this alkylated benzene ring, alkylated only at the primary position and not at the secondary position, which we saw the competing reaction when we did the Friedel-Crafts alkylation instead of the acylation. Polyacylation will not be observed too, so that's another advantage. We don't have to worry about the multi-alkylation that we saw previously. So that's an advantage of doing an alkylation followed by a reduction. So that's going to take us to the end of our electrophilic aromatic substitution reactions on benzene. In our next video, we're going to move on to looking at what happens when we have these electrophilic aromatic substitutions on rings, benzene rings that already have one or more substituents. And that's going to change the way the substitution occurs significantly. So I look forward to seeing you in that next video. See you next time.